Hi, so my name is Hsia, and I mentioned earlier I just started as a postdoc with the leader group at Goddard. But the project I'm going to be talking about today is one of the last bits of work that I did as part of my dissertation here at the University of Colorado in Boulder with the impact group. And this work was done with the help of Noah Hood, Shu Wang, and Mihai Horani, and it's titled Regolith Dust Mobilization in the Presence of a Magnetic Field. And it's recently been accepted at PRE, so if you want all the details, that's where you can check it out. So, big picture stuff first. We know that electrostatic dust lofting is a key process in many Atlas bodies, in particular the moon. It's been used to explain various natural phenomena like the lunar horizon glow, as well as maybe dust sorting or lunar magnetic anomalies. And then in recent years, it's also received some sort of attention because of its potential to help in dust mitigation strategies, which we know plagues the lives of astronauts and their equipment during missions. So a few years ago, some of my colleagues, they presented some work on early attempts at understanding electrostatic dust lofting. And this is a really simple experimental setup. We have a bit of dust. We place it under, it's in a vacuum, then we place it under UV radiation or expose it to plasma, and it starts to loft. Can we play this video, please? So here it is in slow motion, the magic of dust lofting just when you irradiate it. And so by analyzing the trajectories of these dust grains and measuring the charges on them, you can sort of start to back calculate the forces at play here. And the result of this work was the development of the patch charge model. And that's used to explain why dust lofts under these conditions. And so here it is, a simple patch charge model, which is explained as follows. So within the regolith, there are a lot of microcavities between dust grains. And these microcavities, when they are exposed to incoming UV radiation or solar wind plasma, secondary electrons can form within these cavities, and then you start to get a buildup of negative charges. And these charges can build and build so strongly that it overcomes adhesive forces, gravitational forces, and then the dust grains just launch off the dusty surface. So this study seeks to answer the question, well, what happens when you add a magnetic field to this system? And so we design a really simple, straightforward experimental setup as follows. We have a permanent magnet and we place it beneath the dust bit. In this case, it was about 4 centimeters in diameter. And then we put it in a chamber that exposes it to UV radiation. And we see what happens. Could we play this video too? So I don't have a laser dust pointer, but you can sort of already guess where the magnet was placed. It was right in the middle here, pointing upwards. And that's where you see the central spot of dust activity. And then you see this kind of donut-shaped region where there isn't really any dust activity. And then further out again, you start to see more dust activity again. And we can translate this regions of dust activity to heat maps shown here. So once again, here on the left, the dipole magnet is pointed upwards, out of the page, out of the dust bit. But on the right, the magnet is parallel to the dust surface. So it's kind of like embedded this way, and it's pointed top down here. And the really cool thing is not only do we see regions of dust activity on the top and bottom, but it's an asymmetric pattern. And on this particular setup, there's more dust activity on the left side than on the right side. If you flip the magnet north to south, then the image kind of flips about the dipole axis, and then you get a lot of dust activity on the right side, not the left side. And this is so curious and so interesting to us. So what explains, oops, I spoiled it. But what explains this inhibition of dust activity in some regions when you add a magnetic field? And if you do a quick calculation, you'll soon realize that the strength of the magnetic field is too weak to actually be directly affecting the motion of the dust grains themselves. So it is something else. And what we propose is an update to the patch charge model. So in addition to the incoming UV radiation or high energy protons or electrons, we have to consider what ambient electrons are doing in the system. And ambient electrons can be photoelectrons from other parts of the system, or just any electrons just hanging around, and they're represented in my diagram here in green. And if these ambient electrons are allowed to reach the microcavities, then that helps to lower the overall potential within these microcavities, and that results in more negative charges and more chances that the dust is going to loft. And so what the magnetic field does is just inhibit the access of some of these electrons to some of these microcavities. And if you don't get more electrons, then you don't get a lot of dust lofting. So we have a theory, we should test it. And what we did was we did a simple test particle simulation where we tracked ambient electrons in a system that closely mimicked our experimental setup. So here on the left is just a diagram of a comparison between the magnetic field that we measured in our experimental setup versus the magnetic field that we used in our calculations. And then on the right, some of the key parameters used in the simulations, which I will skip over to show you the results. And here we see on the top the same diagram that I showed you earlier. That's the experimental dust landing, dust lofting regions. And here on the bottom, that's where our simulations show electrons are landing within the system. And it's so obvious that there's such a similarity between the two. On the left, again, the magnet is pointing kind of directly out of the page, and you see the central region of high electron activity, and that's because electrons are funneled into the cusp of the magnetic field. And then there's a central region where there's not much activity going on because the lobes are shielding the dust, shielding the electrons from coming in. And further out again, what we get is more electrons landing on the surface because the magnetic field is too weak to affect their motions at all. And on the right here, the magnet is parallel to the surface. And so in the cusp regions of the magnet, once again, we see high electron activity, and that's because the magnetic field is guiding the electrons to their spots. And the asymmetry is caused by the E cross B drift, which pushes the bulk of the electrons to one side. And as we expect, when we flip the dipole, the magnetic poles around, then the E cross B drift goes to the other side, and that explains the dust activity pattern that we are measuring experimentally.
1 minute.
Cool. So we are observing a direct impact of ambient electrons on dust mobilization, and it's revealed by the application of a magnetic field. So this is the conclusion that I'm trying to share with you today. And that's it. Thank you for listening to my talk. If you'd like to know more about what I'm doing at Goddard, we have a poster tomorrow morning, and it's titled The Survivability of Prebiotic Molecules on the Lunar Surface. So if you're interested in that, check it out. Thank you.
Line that I'm going to ask first from Frank Hahn, which is, would the dust respond to magnetic field if they are not charged, i.e. do they have iron elements, etc.?
So part of this is that the dust is expected to be charged, and it's charged because of the patch charge model, right? It's in the air, it's floating because it's charged. So therefore, yeah.
Yeah, so it doesn't start with a charge, but it gets it due to the environment.
Hi, Alicia. I work a lot on Mercury, and Mercury has both an ambient general magnetic field and surface magnet at the poles, and also it has about 10 times as much radiation as at the moon. So would you expect Mercury to be a dustier place? And also, my other question is, how does the grain size affect the lofting?
I'm not a geologist and I don't know what makes dust appear. So I don't know whether Mercury would be dustier than the moon.
Well, I mean, just because of the enhanced UV radiation and the magnetic field.
Would that cause dust to be formed?
Would it cause dust? Well, there is dust there, so would you have more dust lofting at Mercury than at the moon? That was the question.
I think that strongly depends on the configuration of the magnetic field and how it concentrates and does not concentrate and where it orients, and then that would affect how the electrons are moving within the system. So as you saw in our results, some regions had a lot of dust activity and some did not, and that depends on the orientation and strength of the magnetic field.
It would be interesting to model it, I think.
Sounds great. All right, thank you. We'll move on.